Recurrent neural networks, usually called RNNs, were designed to solve a fundamental limitation of standard feedforward neural networks, the inability to naturally model sequential data where order and temporal dependence matter. In many real-world problems such as language, speech, time series, and control systems, the meaning of the current input depends heavily on what came before. Treating each input independently discards critical structure. RNNs introduce a mechanism for maintaining state across time, allowing the network to build representations that evolve as new inputs arrive. At a conceptual level, an RNN is a neural network that is applied repeatedly across the elements of a sequence, with a hidden state that carries information forward. Instead of processing the entire input in one pass like a feedforward network, an RNN processes one time step at a time. At each step, it takes the current input and the previous hidden state, combines them through a learned transformation, and produces a new hidden state and optionally an output. This recursive structure allows the model to accumulate context. Mathematically, the core recurrence can be written as a function where the hidden state at time t is a nonlinear transformation of the input at time t and the hidden state at time t-1. The same set of weights is reused at every time step. This weight sharing across time is analogous to the spatial weight sharing in convolutional networks. It dramatically reduces the number of parameters and encodes the inductive bias that the same transition dynamics apply throughout the sequence. To understand why this matters, consider language modeling. The probability of the next word depends on the previous words. An RNN processes the sentence word by word, updating its hidden state to reflect the evolving context. In principle, the hidden state can summarize arbitrarily long histories, although in practice this turns out to be challenging. The hidden state is the central object in an RNN. It acts as a compressed memory of everything the network has seen so far. However, this memory is not explicitly structured, it is a vector of real numbers learned through gradient descent. The network must learn how to encode and retrieve useful information from this vector over time. This is one of the reasons RNN training can be difficult. Training RNNs uses backpropagation through time, often abbreviated as BPTT. Conceptually, the recurrent network is unrolled across the sequence length, producing a deep computational graph where each time step corresponds to another layer in depth. Gradients are then propagated backward through this unrolled graph. Because weights are shared across time steps, gradients from all steps accumulate into the same parameter updates. Backpropagation through time introduces one of the most famous technical challenges in deep learning, the vanishing and exploding gradient problem. As gradients are propagated through many time steps, they are repeatedly multiplied by the recurrent weight matrices and activation derivatives. If the spectral radius of these transformations is less than 1, gradients shrink exponentially. If greater than 1, they grow exponentially. Both cases make learning long-range dependencies extremely difficult. This problem explains why early vanilla RNNs struggled with tasks requiring long context. Although theoretically capable of modeling long sequences, in practice they tended to focus on short-term dependencies because gradients from distant time steps became too small to influence learning. To mitigate exploding gradients, practitioners often use gradient clipping. This technique rescales gradients when their norm exceeds a threshold, preventing unstable updates. Gradient clipping is simple but effective and remains standard practice when training recurrent models. The vanishing gradient problem required more structural innovation. This led to the development of gated recurrent architectures, most notably the long short-term memory network, or LSTM, and the gated recurrent unit, or GRU. These architectures introduce gating mechanisms that allow the network to control information flow across time more effectively. The key insight behind gating is to create paths through time where gradients can flow with linear attenuation. In an LSTM, the cell state acts as a kind of highway for information, with gates that regulate what information is added, removed, or exposed. The forget gate determines what fraction of previous memory to retain. The input gate controls how much new information to write. The output gate controls what part of the memory becomes visible to the next layer. These gates are implemented using sigmoid activations that produce values between 0 and 1, effectively acting as soft switches. Because the cell state update includes an additive component rather than purely multiplicative recurrence, gradients can propagate more stably across long sequences. This design dramatically improved the ability of recurrent networks to model long-range dependencies. GRUs simplify the LSTM architecture by combining some gates and reducing parameter count. They often perform comparably to LSTMs while being computationally cheaper. The choice between LSTM and GRU is often empirical and task-dependent. Another important design dimension in RNNs is whether the model processes sequences in one direction or both. Standard RNNs are unidirectional, meaning the hidden state depends only on past inputs. Bidirectional RNNs process the sequence in both forward and backward directions and concatenate the hidden states. This allows the model to use both past and future contexts when making predictions, which is useful in tasks like sequence labeling where the entire sequence is available. However, bidirectional models cannot be used in streaming or real-time settings where future inputs are not yet known. This highlights an important trade-off between context and causality. Sequence length handling is another practical issue. Real-world sequences often vary in length. In batch training, sequences are typically padded to a common length, and masking is used to ensure that padded positions do not contribute to the loss. Efficient batching and masking are essential for high-throughput training of recurrent models. Teacher forcing is commonly used during training for sequence generation tasks. Instead of feeding the model's own previous prediction as input at the next time step, the ground truth token is used. It stabilizes training but creates exposure bias. At inference time, the model must rely on its own potentially imperfect outputs. Various techniques such as scheduled sampling attempt to mitigate this mismatch. RNNs can be configured in several input-output modes depending on the task. In many-to-one setups, the model consumes a sequence and produces a single output, as in sentiment classification. In one-to-many setups, a single input produces a sequence, as in some generative tasks. In many-to-many setups, outputs are produced at every time step, as in sequence labeling or machine translation. Understanding these modes is important when designing model architectures. Stacking multiple recurrent layers increases representational power. In a stacked RNN, the hidden state sequence from one layer becomes the input sequence to the next. Deeper recurrent networks can capture more abstract temporal patterns but are harder to train and more computationally expensive. Regularization in RNNs has its own nuances. Standard dropout applied independently at each time step can inject excessive noise into the recurrent dynamics. Variants such as variational dropout apply the same dropout mask across time to preserve temporal coherence. Careful regularization is important to prevent overfitting without destabilizing training. From a computational standpoint, RNNs have an inherent sequential dependency. Each time step depends on the previous hidden state, which limits parallelization across time. This makes RNN training slower on modern hardware compared to architectures that allow full parallelism across sequence positions. This limitation is one of the major reasons attention-based models later gained prominence. Despite this, RNNs remain valuable in certain contexts, especially when sequence lengths are very long or when strict causality and low latency streaming are required. Their constant memory hidden state can be advantageous compared to attention mechanisms whose memory grows with sequence length. Another important concept is the distinction between hidden state and output state. In some tasks, only the final hidden state is used for prediction. In others, outputs are produced at each time step. Careful architectural design determines how information flows from the recurrent core to the prediction head. Initialization of the hidden state also matters. It is often set to zeros, but learned initial states or context-dependent initialization can improve performance in some applications. For very long sequences, truncated backpropagation through time is commonly used, where gradients are propagated only across a fixed window rather than the entire sequence. This reduces memory and compute cost but limits the effective context length the model can learn. In practical deployments, RNNs are widely used in speech recognition, time series forecasting, anomaly detection, and certain control problems. They were historically dominant in natural language processing tasks such as language modeling and machine translation before the rise of transformer architectures. Understanding why transformers eventually overtook RNNs is instructive. The main advantage of attention-based models is their ability to model long-range dependencies without sequential computation. They allow full parallelization across sequence positions and provide direct paths between distant tokens. However, this does not invalidate the conceptual importance of RNNs. Many ideas in sequence modeling were first explored in the recurrent framework. There is also ongoing research into hybrid architectures that combine recurrence with attention or convolution. Some modern state space sequence models can be viewed as continuous time generalizations of recurrent dynamics. The core idea of maintaining a learned state that evolves over time remains fundamental. For a technically sophisticated audience, the most important mental model is that RNNs implement a discrete time dynamical system with learned parameters. The hidden state is the system state, the recurrence defines the transition function, and training adjusts the dynamics to capture statistical structure in sequences. Thinking in dynamical systems terms often clarifies stability, memory, and gradient flow behavior. Ultimately, recurrent neural networks represent a crucial step in the evolution of deep learning architectures. They formalized how neural networks can process sequences and maintain memory over time. Even though newer architectures have surpassed them in many benchmarks, the principles underlying RNNs continue to influence modern sequence modeling research. A deep understanding of recurrence, gating, and backpropagation through time remains essential for anyone working seriously in AI systems and temporal modeling.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.